Hi, my name is Sid Gupta, and I'm a first year student from Charlotte, North Carolina. A few fun facts about me are that I like to play basketball, and I'm a very sociable person, which plays well into why I want to be a ULA. This summer, I'm going to be an orientation leader, being students' first connection into the Carolina community. On top of that, I currently volunteer on this online platform known as Learn to Be, in which I teach students a variety of topics. Currently, I teach one of my students chemistry. And I realized that I enjoy teaching chemistry. I'm very passionate about it. Anything that reflects in my teaching style. I try to emphasize to my students that learning about it is not only about understanding and just doing problems, it's more about appreciating how much it brings into our daily lives. And that's something I want to bring into my chemistry ULA. And I also want to be able to welcome students into Carolina as well, as I want to teach Chem 102, which is primarily a first year course. And how I'll teach students chemistry. I plan to bring students into the realm of bridging concepts together. I was speaking to Dr. Zukovitsky a few days ago, and he told me his favorite part about teaching is watching students connect concepts together. And I think that's also a great way to learn and to advance your own personal understanding. Because to be able to connect two concepts together, you have to understand both of them very, very well. And that'll also help you on tests when you encounter questions you may not know that well, and just other classes in general. And that's what I plan to bring to the table and help students. Okay, so now we're going to work through the following problem. Ammonium nitrate dissolves readily in water at room temperature even though the dissolution is endothermic, requiring 26.4 kilojoules per mole of energy. The entropy of dissolution is 109 joules per Kelvin mole. At what temperature, degrees Celsius, does the dissolution process stop being spontaneous? And so, what we're going to have to realize is what we're working with regarding this problem. We're working with endothermic reactions, which means we're working with delta H, or enthalpy, and we're working with entropy. It's also asking us about spontaneity, which means we're going to have to use something involving delta G. And so I'm going to write that at the top, where we're going to delta H, delta S, and delta G. And so let's look at what it's asking us to do. When it's asking us about spontaneity, we know that it's going to do something with delta G. And when does something stop being spontaneous? When delta G is equal to 0. When it's equal to 0, the reaction is at equilibrium, meaning that it doesn't want to proceed anymore. And so next, we have to connect all of these concepts together. And how do we do that? It's with this following formula. Delta G is equal to delta H of the system minus T times delta S of the system. And so now that we know what we're working with, let's see what else we have to do. So the first thing I'm going to do is I'm also going to equal this formula to 0 because we know that delta G equals 0 when the reaction stops being spontaneous. And now we're going to be able to plug in our numbers and see what we're working with. And so I'm going to take a double look at our numbers. We're working with 26.4 kilojoules per mole and 109 joules per Kelvin mole. However, when we're looking at it, joules and kilojoules are not the same units. So we're going to have to switch them around. I want to work with kilojoules, so I'm going to turn 109 joules per Kelvin mole to 0.109 kilojoules per Kelvin mole. And so now that we have that done, let's see what else we have to do. I'm going to now plug everything into our equation. And just as a double check, we know that 26.4 kilojoules per mole refers to enthalpy. So I'm going to write delta H. And we also know that 0.109 kilojoules per Kelvin mole refers to entropy. So I'm going to write entropy, or delta S. And so now, let's plug everything into our equation. I'm going to write 26.4 kilojoules per mole is minus T times 0.109 kilojoules per Kelvin mole equals 0. And so now we're going to start solving. However, I want to point out a few things. We want to make sure we get the right amount of significant figures. And so we know it's going to involve some addition and subtraction, and we know the rules. So I'm going to come back to that later, but I want you to be aware of that as you work through the problem. So now when we're solving for T, we know when we plug in, it's going to end up being negative 26.4 over negative 0.109, and that is equal to 242.2 Kelvin. But remember, we want it in Celsius. And how do we do that? We subtract 242.2 Kelvin minus 273.15 degrees Kelvin, which is equal to 31 point something degrees Celsius. And so now let's look at our significant figures. We know when we're working that we are doing addition and subtraction and both multiplication and division. So because of that, we know when we're subtracting, we want to keep the least number of decimal places. And so when we're looking at our problem, we realize that, originally it was 109 with 0 decimal places. And now when we're looking at it, even though we put in 0.109, it's really still 109 joules per Kelvin. So when we're subtracting, we're going to want to make sure there's 0 decimal places. That's what leads us to 31 degrees Celsius. Thank you.